Hello guys, and welcome back to Introduction to Number Theory. Now we will discuss the uniqueness of the decomposition into prime factors, and I am going to prove that in Euclidean rings this decomposition of any element is actually unique. So we already know what uniqueness means, but let me just remind you. This means that if we take any element, call it n, and it has some decomposition into prime factors, say p1, p2, p3, and so on, pk, where we do not suppose that all these prime factors are different, so they may be equal factors among them. And at the same time, n has some other decomposition into prime factors q1 multiplied by q2 multiplied by q3 and so on multiplied by ql, where we do not suppose that we have equal amounts of prime numbers here and here. Then the uniqueness of the decomposition means that, first of all, there are equal amounts of primes here and here, so k is equal to L, and also that there is a permutation, denote this number k, and also that there is a permutation, call it sigma. It's a permutation of k numbers, such that for every number we have such that for every number I, the ith number prime element in the first decomposition is equal to some element in the second decomposition, but this some element is what we use this permutation for, so we write sigma of I. So we do not know which element this is, but we certainly know that all these elements, when permutated in some order, must be equal to these elements. But this is not quite so. I wrote equality here, but actually I meant that these two numbers must be not necessarily equal, but associated to each other. This is a standard mistake which may be done by many people. So I will write it correctly. We say that pi is associated with q sigma of I. I remind you that being associated means that this means that, say, pi is equal to this element here multiplied by some reversible element, or we call them sometimes unity or units, which means an element such that there is another element which multiplied by this epsilon gives 1. Gives us unity. So once more, the uniqueness of decomposition into prime factors means that if we have two decompositions, then the number of prime factors must be equal in both of them. They must be equal to each other. And in some order, prime factors in the first decomposition coincide with prime factors in the second decomposition, where by coincide we actually mean that are associated with. So very many different points here. Just try to keep them all in mind. And now we will simply try to prove this. But first of all, I would like to remind you of a very important property of prime elements, which we'll be using in our proof. This property is actually a definition of prime elements. Well, we say that P is prime if for arbitrary elements A and B, from the fact that AB is divisible by P, it follows that either A or B must be divisible by P. So once again, we say that P is prime if from this it follows this. It follows that either first factor or the second factor of this product is divisible by P. Now let's try to use this and some common sense to prove the uniqueness of the decomposition. And I just remind you that we are now inside the arbitrary Euclidean ring. So let's go on. First of all, notice that P1, being an element of the first decomposition, is a divisor of the second decomposition. P1 is a divisor of Q1 multiplied by Q2 multiplied by Q3 and so on multiplied by QL. I will still denote the number of primes in the second decomposition by L because I still, for now, do not know whether it is equal to K or not. And now we use the property of prime numbers and just look at this big product as a product of two elements. First of them is Q1, and the second one is the product of all other elements in this expression. So this is, in some sense, A, and this is B. So we have that AB is divisible by P1, A multiplied by B is divisible by P1. So we understand that it means that either A is divisible by P1 or B is divisible by P1. Okay, so now let's create a tree, a tree of cases, because because this means that since Q1 is A and B is this expression here, this means that either Q1 is divisible by P1. Let's write it this way. So either Q1 is divisible by P1, which is actually the same as this statement here, or we have that Q2 multiplied by Q3 multiplied by and so on multiplied by QL. Maybe this guy here is divisible by P1. In the first case, where Q1 is divisible by P1, we understand that these two prime elements are the same, but the same only in the sense of the being associated. So we can write that P1 is equal to Q1 multiplied by some reversible element. And over here, we have some product of a rather large number of elements divisible by P1. But we can apply the same method and consider this as a product of two elements. This is the first one. We call it A, because the previous A is now we're not interested in it. We throw it away. And this is our new element A, and this is our new element B, and their product is divisible by P1. Okay, so we understand that since P1 is still prime, we understand that it means that either Q2 is divisible by P1 or the product of these elements is divisible by P1. I believe that by now you already understood what will happen furthermore. I understand that from the first case we have that P1 is associated with Q2. So we can write that P1 is equal to Q2 multiplied by some epsilon, where epsilon still denotes a reversible element. Or from here we'll have several other cases, either Q3, either Q3 or all other elements, and so on and so on. And eventually we will certainly find such an element in the second decomposition, where I call this decomposition the second one. We'll certainly find such an element of the second decomposition, which will be associated with P1. Just P1 for now. Well, let's suppose that we have some element Q with number S, which is associated to P1, which means that P1 is equal to Qs multiplied by an epsilon, where, well, this epsilon, we have many of them here, but we understand that actually now we find only one of them, and there is only one of them for P1. So P1, well, we can just say that P1 is equal to Qs multiplied by epsilon 1. What now? Okay, so we found an element of the second decomposition associated with the first element of the first decomposition. What should we do now? And now that we have P1 is associated with one of the prime factors of the second decomposition, we can apply this, the original decompositions, both of them. And we understand that P1 is present over here. And somewhere inside the second decomposition we have Qs, well, P1 we have in the first decomposition, and Qs we have in the second decomposition. Well, somewhere over here, we don't know where. And now we can divide both these decompositions by P1. Well, these are decompositions of the same number n. So simply divide n by P1. Simply divide n by P1. And on one hand, it is equal to P2 multiplied by P3 multiplied by, and so on, multiplied by Pk. On the second hand, n divided by P1 is equal to Q1 multiplied by Q2 multiplied by, and so on, until we get to Qs, where we have Qs minus 1, and we have Qs over here. I will write it a bit later. And then we have Qs plus 1, and so on until we get to Ql. And what do we have here instead of Qs? Let's take it. Let's see. Well, we understand that we divide everything by P1, and dividing by P1 is equivalent to dividing by Qs multiplied by epsilon 1. So here we had Qs, and now we divided it by Qs, and we also divided it by epsilon 1. So here we have something like 1 over epsilon 1. And since we understand that epsilon 1 is a reversible element, so we understand that this is also an element of our ring. And we understand that it's also reversible. So it turns out that the number of factors in this decomposition here has decreased by 1, and the number of factors in this decomposition here seems to not have changed, but it is not so, because all these elements are prime, except for the yellow one, which is actually just some reversible element. So we can simply pack it into one of other elements, say this one, and denote the element q as minus 1 over epsilon 1, denoted by q as minus 1 with a hat. It's another prime element. Why is it prime? Because it is associated with q as minus 1. So this way we have decreased the number of elements in the second decomposition also by 1. Now we have a new number, n over p1, which has two decompositions, the first one and the second one. These two decompositions have less factors than the original two decompositions, and we can continue using the same methods, the same algorithm, applying it to the new decompositions of the new number, and eventually we will come up with a situation where one of the decompositions is out of prime factors. Well, since we are decreasing the number of prime factors by 1 every time we use this method, eventually we will come up with a situation when one of these decompositions is out of prime factors. And since both decompositions represent the same element, the same number, we can say so, then at the very same moment when one of the decompositions is out of prime factors, then the second one must also be empty, must also have no prime factors whatsoever, which will prove that in the original situation where we had two decompositions, the number of prime factors were equal. And this was the first part. And the second part, we understand that we need to prove that there is a permutation which pairs primes from the first decompositions with primes from the second decomposition into pairs of associated prime factors. And this is also true because every time we shortened these decompositions, we did it by finding a pair of associated prime factors, one from the first decomposition and the other one from the second. So we got rid of these pairs of associated prime factors, and eventually both decompositions turned out to be empty. Well, this by all means that indeed the decomposition into prime factors is actually unique.